everybody. Welcome back to Measure Theoretic Probability. When we last left off, I know it's been a while, we were talking about simple random variables. A random variable is a measurable function from a probability space into the real numbers. I will remind you in a few moments what that means, but a simple random variable was a random variable that can take on only a finite number of values. In today's video, I want to focus on non-simple general random variables. So the first thing I want to do is take a step back and outside of all probability spaces. Suppose you have a non-empty set omega-1 equipped with a sigma field curly F1. And suppose that you have another non-empty set omega-2 equipped with its own sigma field curly F2. I'd like you to consider a mapping F that takes in points in omega-1 and returns points in omega-2. So I don't have a probability space here. What I have are two measurable spaces. They do not have measures yet, although they could, and I'm talking really generally, so I might call the measure on the first space mu1 and the measure on the second space mu2. A function f from omega-1 to omega-2 is said to be measurable f1 slash f2 if the inverse image of any set from curly f2 pulls back and is a set in curly F1. So we've seen this sort of thing a lot, but we haven't used this full terminology. We've just said F is measurable, but because it's intricately linked to the sigma fields, it is important, if there's any confusion, to say measurable curly F1 slash curly F2, something like that. So let's get back to actual random variables. Suppose I have a probability space, an omega, and a curly F. And it's not a probability space until I put a probability measure on it. But just like that last definition, I don't need a measure for what I'm about to talk about. So put in a probability measure P there if it makes you feel better. But the secondary space when we're talking about random variables is going to be that it takes points in omega and the function x and maps them into the real numbers. And we have a sigma field on our omega and the sigma field on the real numbers. That is by and far the most popular sigma field that is in use on the real numbers is the Borel sigma field or Borel sigma algebra. That is the default sigma field on the reals, unless something is explicitly stated otherwise. We talked about the Borel sigma field back early on in this course, maybe in video 2 or 3, and I called it curly B or something like this. I'm now going to call it curly B of the reals, because in today's lecture, I want to increase the dimension and talk about Borel sets on R2 and R3 and, on higher dimensional spaces. So I need more B's, if you will. So I'm going to write this curly B of R to talk about the Borel sets on the one-dimensional reals. Now, a function x taking points in omega and giving you real numbers is a random variable if it is measurable. In our new terminology, we would say if it is measurable, curly F slash the Borel sets on the reals. But this is very clunky. And usually when we have a probability space and a random variable, the second space is assumed to be reals and Borel sets, and we don't bother to say this part. We just say that it's a random variable if it's a function from omega-1 to omega-2 that is measurable. You'll recall measurability means that if you take any set in the sort of target sigma field, which right now is the Borel set. So take any Borel set and look at the inverse image under the x function, which is the points in omega that mapped into that set. That inverse image set needs to be in curly F. That is the measurability condition. Today, we are going to be talking, as I said, about higher dimensional Borel sets. So I'd just like to remind you really quickly that we define Borel sets, or the Borel sigma field or sigma algebra on the reals, as the sigma field generated by all open intervals of the form open A to open B. However, we showed back then when we were talking about Borel sets that we could equivalently generate the same sigma field using closed intervals like closed A to closed B, or half open and half closed like this or this. We even saw that we could generate Borel sets using an interval like open A to infinity or negative infinity to A open, or both of those with the closed endpoint on the A's. All of these were ways that we showed we could equivalently generate Borel sets. And these are not exhaustive, so there are other possibilities here. The fact that we can generate Borel sets in many different ways is going to be an important theme today because we're going to have at a very exciting lemma. Actually, it's coming up next, so let me stop talking about it and get into it. Suppose I have a non-empty set omega 1 and a non-empty set omega 2. And suppose I have a mapping or function f that takes in points from omega 1 and returns points in omega 2. Suppose I have a sigma field curly f1 on omega 1. Now, I am representing this sigma field with a bunch of shaded looking sets here. This is just a depiction for me to talk about this. This is not an accurate depiction, as it usually is not in my videos. Because if this is in curly f, then the complement in omega 1, which is everything outside of this particular set, should be there as well as the entire omega. And I clearly haven't shaded the entire omega. So these sets that I've shaded here are supposed to represent the sets in the sigma field curly f1, but it's not an accurate depiction by any means. So suppose in omega 2, we have a sigma field curly f2 represented by sets that maybe look like this. And then for the second sigma field, I want to get just a little more specific. I want to talk about a generating collection of sets, a curly A. So I'm going to divide these sets up into some yellow sets, which I'm going to call curly A sets. This is just a collection of sets. And then green sets, which are the ones we needed to fill in to turn curly A into a sigma field. So what I have here are two spaces, an omega 1 and omega 2. I have a sigma field curly f1 and a sigma field curly f2, but I'm assuming that curly f2 is generated by this collection of sets, curly A. Okay, so in words, what I just said, we have these two spaces. We've got a mapping f from omega 1 to omega 2. I'm assuming curly f2 is the sigma field generated by curly A, and that lives over on the omega 2 set. So the punchline to this lemma says that if the inverse image of sets from curly A pull back and are in the original space 1 sigma field curly f1, then everything in the full sigma field generated by curly A, that is everything in curly f2, will necessarily pull back to be in curly f1, which is an awesome and powerful result for us to show that things are measurable because we can restrict our attention to just pulling back a subcollection of sets, the generating collection for the relevant sigma field in the second space. Let's prove it. This proof is quite short if you take one claim to be true. I'm going to start out by assuming this is true, so that the inverse image of sets A from the generating collection of sets for the second sigma field, I'm going to assume they pull back under F into the original sigma field. And I'm going to define a collection of sets, curly M, to be subsets. This doesn't involve the sigma field at this point, but to be any subsets of omega 2 for which the inverse image under F falls into the sigma field curly F1. Now, we already know that curly A is contained in curly M because by the setup of this proof, we know that everything in curly A does pull back into curly F1. And this collection M is everything that pulls back into curly F1. So the sets in curly A definitely do that. So curly A is contained in the set or class M. I claim that it is routine. Whether or not you think it's easy is a different matter, but pretty routine to show that this curly M is a sigma field. You have to show it contains the full omega, that it's closed under complements, and that it's closed under countable unions of sets in curly M. And these are fairly straightforward. And because I will be showing other things are sigma fields today and going through those three properties many more times, I'm going to leave this one out and leave it to you. So let me know in the description box if you're having trouble showing this fact, and I will come back to it. So we've got curly A contained in curly M. Curly M is a sigma field. The sigma field generated by curly A is our definition of curly F2. And the sigma field generated by A is the smallest sigma field containing all the sets in A. Curly M is a sigma field containing all the sets in A. This means that curly F2, which is the sigma field generated by curly A, has to be contained in curly M because this, by definition, is the smallest sigma field that contains curly A. Now, if you look at the definition of curly M, we now see that for every set in F2, which is the sigma field generated by curly A, that will pull back under the function f to a set in the sigma field curly F1, and that's what we wanted to show, so we're done with this proof. Okay, so again, a random variable is a measurable function from a probability space into the reals. And yes, again, this doesn't look like a probability space until I put a probability measure on it, until I have the omega and the f and the p. But I actually don't need this measure for what I'm about to state. So one more time, if this bothers you, fill these out. Make this a complete measure space with the omega, the curly f, and the probability measure p. And then make this one a complete measure space with the reals, the Borel sets, and maybe a Lebesgue measure. It doesn't matter. We know that x is a random variable if it is measurable, if it's a measurable function from this space to this space. But what we're going to learn now is that x is measurable if and only if sets like this are in curly f for every little x in the reals. So all omegas such that x of omega is less than or equal to x needs to pull back into f. Another way to write this set right here is x inverse of the interval from minus infinity up to x closed on that right side. Let's prove this. One direction is super straightforward. If I assume that x is a random variable and therefore a measurable function, that means that the inverse image of all Borel sets in the second space pull back under the function x, and the inverse image under x is in curly f. That is the definition of measurability, and measurability is the definition of a random variable. So assuming we have this, we definitely have these sets pulling back into sets in the sigma field curly f, because these are Borel sets. So if the inverse image of all Borel sets fall in curly f, then the inverse image of sets like this fall in curly f, no matter what real number little x you choose. So we have what we wanted, and we're done with the forward direction for this proof. So let's go the other way. Here is just the recap. And now I'm going to assume that the inverse image of sets like this are in curly f, no matter what real number little x you choose. To show that x is a random variable, we don't just want this to be true, we want to pull back any possible Borel set, which could look very strange. And we want that pullback to be in curly f. But we know that Borel sets can be generated by sets of this form. And today's lemma tells us that if the inverse image of these generating sets are in the sigma field in the first space, then the inverse image of all sets in that second sigma field are in the original sigma field. And we're done. We have then that inverse images of Borel sets under x fall into the original sigma field curly f, and that x is a random variable. Recall again that we can generate the Borel sets on R by intervals like these, and this is not an exhaustive list. And you can replace the A and the B with an X and a Y if you want this to sort of match up better with some of the theorems from today. But we already know right now that the second part, the last theorem, was an if and only if. The second condition can be replaced by pulling back any of these types of sets. For example, we now have the theorem that x is a random variable if and only if the inverse image of all open intervals of the form open x to open y are in F. And that is because these types of intervals form a generating class of sets for Borel sets, and we can apply that lemma. And the proof is exactly the same as the proof of the previous theorem. So you'll see that previous theorem, which says that x is a random variable if and only if the inverse image of those sets from minus infinity to closed x pull back correctly. But we can replace that interval with all different types of intervals as long as the types we use can be used to generate all Borel sets. So let's talk sigma fields. We already have, but now that we are talking more generally and away from simple random variables, I need to say a few more things. So recall that the sigma field generated by a random variable x, which we're going to denote by a sigma of x, is defined as the smallest sigma field with respect to which x is measurable. For simple random variables, we were able to construct such a sigma field by looking at the finite range, the finite number of values that the mapping x could produce and pulling them back, and then considering any subsets of R in the second space and seeing if no points fell in there, if one of those range points fell in there, if two, and pulling those back. It's going to be just slightly more complicated here. But this is the theorem we had back then. So back when we had simple random variables, we saw that we could characterize the sigma field generated by X as the inverse image of sets of all subsets of R. We also saw that any simple random variable Y is measurable with respect to the sigma field generated by X, if and only if there's some map from R to R, such that Y can be represented as f of X. So today, I want to take away simple. And what is that going to change in the rest of the theorem? These H's, any subsets of R, this is going to be replaced with I need H to be a Borel set on R. So in other words, we can now characterize the sigma field generated by any random variable X by looking at every possible Borel set in R and pulling it back into the original probability space and collecting those sets. That will form the sigma field generated by X. And the second one here, the second part of this theorem, the only thing I have to change is this f does need to be a measurable function. So pretty similar. And as you might guess, this theorem can be used even in the simple case. So this is a more restrictive theorem, but it will work in the simple case as well. We're going to prove this, I think, in the next video. What I'm waiting for is to bring in vector-valued random variables in the general non-simple case. Then I can restate this theorem, and then we can prove it then for more general dimensions, which will include one-dimensional random variables. So what is a vector-valued random variable? Again, I've used the word again quite a bit today. This is something we have talked about, but not really formally in the general case. So we were talking about simple random variables, and I did say some things a little bit generally. So this might be a bit of a repeat. But a k-dimensional random variable, a vector-valued random variable with components x1, x2 out through xk, this is a function that's going to take a single point in omega. So you would evaluate this vector. It would be like an x1 of omega, comma x2 of omega, comma x3 of omega out through xk of omega. And those components would each produce a real number. So this is representing a function from omega into Rk, into the k-dimensional reals. The spaces under consideration here are some initial omega with a sigma field f, and then Rk, the k-dimensional reals, equipped with the Borel sigma field on the k-dimensional reals. In order for this vector to be a random vector or vector-valued random variable, we need inverse images of all Borel sets on Rk to pull back into the original sigma field on the initiating space, the omega and the curly f. So nothing's really new, but because of this, I think we need to talk about Borel sets in higher dimensions. Just a quick couple of reminders. The Cartesian product, if you have sets A and B, then A cross B consists of all ordered pairs, a little a comma little b, where little a comes from A and little b comes from B. This is, again, a Cartesian product. And then if you see entire collections or classes of sets, curly A and some kind of curly B that is not necessarily Borel sets, and you cross those, this is the collection of sets like this. The Borel sets on R2 is the sigma field or sigma algebra generated by all open intervals of the form from A to B, an open interval crossed with a C to D, an open interval on like the y-axis, so like an open rectangle. And I'm not going to write this for R3 because it's the same thing, but I have to put on another interval. And for Rk, the same thing. So the Borel sigma field on Rk is the smallest sigma field generated by a cross product of rectangles, like a little a1 to little b1, crossed with a little a2 to little b2, crossed with out to a little ak and a little bk. I think if you get it for 2 dimensions, you get it for k dimensions. In hopes on getting a handle on what the Borel sets in R2 look like, I claim that the Borel sets in R2 are the same as if you take all the Borel sets in R1 and you cross them with all the Borel sets in R1. So we just talked on the previous slide about the cross product of classes of sets. That is not a sigma field, but if you then generate a sigma field from that, that is one way to get the Borel sets on R2. So this sigma field generated by this cross product is often denoted like this, as the Borel sets on R, and then this cross with this circle around it, and the Borel sets on R. I'm not going to write this because this can be confused with a Kronecker product of matrices. This symbol is not exclusive to this sort of thing. But if you're reading any literature on measure theory, especially a measure theory book, if you see this, it most likely means a sigma field generated by a cross product of collections of sets like this. So let's prove it. I'm going to show this direction first. I'm going to show that the Borel sets on R2 are contained in the sigma field generated by the cross product of 2 one-dimensional collection of Borel sets. So consider any rectangle from like open AB crossed with open CD. This is an open rectangle in R2. Now open AB and open CD, these are both one-dimensional Borel sets. So these are both in the Borel sets on R. And this means, by definition of our cross product of collections of sets, that the rectangle here, this AB cross CD, is contained in the cross product of the 2 collections of one-dimensional Borel sets. If this is in here, then this is in the bigger collection, which you get by taking this group of sets and generating a sigma field. In other words, AB cross CD is contained in the sigma field generated by this cross product. But the B of R2 up here, the Borel sets on R2, this is defined to be the smallest sigma field that contains all such rectangles. So this is a sigma field containing such rectangles. This is the smallest, and therefore this Borel sets on R2 has to be contained in this set right here. Okay, so now I want to show the other direction. This one's a little bit more work. I want to show that the sigma field generated by the cross product of 2 collections of one-dimensional Borel sets is contained in the Borel sets on R2. I'm going to start off by defining a collection of sets, curly A, to be all subsets A of R, such that A crossed with the entire real line is in the Borel sets on R2. I claim that curly A is a sigma field. You might want to skip this one, just like I skipped the last sigma field claim, but I chose to show this one, so let's do it. We have 3 things. The first thing we want to show is that A contains the full omega. So the hardest part, I think, about this right here is, what is the full omega? That is the full space of elements, and in this case, the full omega is the real number line. That's the space we're working in. So I want to show that the full real line R is in curly A, which means I want to show that R cross R is in the Borel sets on R2. But R cross R is how we define the 2-dimensional reals R2, and the Borel sets on R2 is a sigma field on R2. So it has to contain its omega, which is R2. So R cross R, which is R2, is definitely in the Borel sets on R2. And that means that the real line is included in curly A. So we've got part 1 of the definition of a sigma field. So now let's show that curly A is closed under complements. I'm going to grab a set A in curly A, and this means that A crossed with the reals has to be in the Borel sets on R2. So here is R2. This x-axis is R1. By these green segments and dots here, I'm representing a set A. So it looks like my set A is the union of 2 intervals and a point. I don't know if these intervals are open or closed. I don't really care. But if A is coming out of curly A, as we're supposing, then A crossed with R is going to look something like this. It's just going to expand those intervals and dots and bring in the y-axis, or the x2 axis. If A came out of curly A, by definition of curly A, we know that this set depicted in green here must be in the Borel sigma field on R2. If you go back to my previous picture with just the two intervals and the dot, and imagine on the x-axis the complement of that, then if you multiply that stuff by r, you're going to fill in the vertical bands all around the vertical green stuff here. In other words, a complement crossed with the reals is the same thing as a crossed with the reals and then complemented. We already know that a crossed with the reals is in the Borel set, the Borel sets on R2. Because the Borel sets on R2 is a sigma field, we know then that the complement of a crossed with r is in there as well. And again, this is equivalent to a complement crossed with r. If a complement crossed with r is in the Borel sets on R2, that means that a complement is in curly A. So we're done with step 2 of showing that curly A is a sigma field. The third and final thing to show that curly A is a sigma field is that we want to show that it's closed under countable unions. So take any sets capital A1, A2, A3, etc. from curly A. By definition, this means that capital A1 crossed with R and capital A2 crossed with R, etc. These are in the Borel sets on R2. So picture an x-axis, or R1 again, and picture a set A1 on the x-axis in R. It doesn't have to be an interval. It could be quite a wild set. But just for simplicity, picture A1, capital A1, as an interval on the real line, and capital A2 as another interval on the real line. They may overlap, they may not. If you union those, you have two intervals on the real line, and if you cross that with R, you get two vertical strips. On the other hand, if you take just A1 and cross that with R, you get a vertical strip. And if you take A2 and cross it with R, you get a vertical strip. And if you union those, you get the same thing. So it doesn't matter if you union the two intervals and then grab the y-axis part, or you take each interval and grab the y-axis part and then union those. You get the same thing. What I'm trying to say is that the union of the ANs crossed with R is the same thing as the union of quantity AN crossed with R. And this is in the Borel sigma field on R2 because we are under the assumption that all these individual sets are, and now we're looking at a countable union of things from a sigma field. There again in the sigma field. And so because this is in BR2, we have shown that this union here is contained in curly A, and we're done showing that curly A is a sigma field. Okay, so now that we've shown that curly A is a sigma field, I want you to note that curly A contains all intervals of the form open A to open B, because open A to open B crossed with the reals, I claim, is in the Borel sigma field on R2. Why is that? I am going to cross open A, open B on that x-axis with the entire vertical strip of the y-axis. And I can write this in many ways. I'm going to write that strip as a union of the interval from -1 to 1, and then -2 to 2, and -3 to 3. It's a little clunky, but it works. And this cross product is the same as the union of AB crossed with each of those intervals. So again, imagine one interval on the x-axis crossed with that entire strip versus that interval on the x-axis crossed with a piece of the strip and a bigger piece and a bigger piece and all unioned. You get the same thing. So this interval right in here, AB crossed with -NN, is definitely in the Borel sets on R2 because this is one of those generating sets. It's a cross product of two open rectangles. And because this is a countable union, this entire thing is in BR2. And if this entire thing is in BR2, then by definition of curly A, this set here must be in curly A. Let's bring it on home. This part of the proof has gone on entirely too long. We have established that curly A is a sigma field. It's on R. It contains all open intervals and more, but open intervals of the form open A to open B. This means that the Borel sets on R must be contained in A because the Borel sets on R is the smallest sigma field that contains these open intervals on R. If the Borel sets on R are contained in A, we have just shown that for any set A in the Borel sets on R, A cross R is in the Borel sets on R2, because this was what it meant to be in curly A, and everything in the Borel sets on R is in curly A. Similarly, for any Borel set B on R, we have shown, by a symmetry argument, that the real line crossed with B is in the Borel sets on R2. What does this get us? Take any Borel sets, capital A and capital B. These could be very strange sets. These are not rectangles or intervals necessarily. If you take A cross B, you're talking about some subset of R2. And I claim that you can get this by taking A crossed with R intersected with R crossed with B. So in a picture here, I'm going to make capital A and capital B look like intervals just to draw a clean picture, but they are not supposed to be nice intervals or rectangles. But note that I could get this region in here, crossing this with this, by intersecting this entire strip with this entire strip. That's what this equality is saying right here. Because these individual sets are in the Borel sets on R2, this finite intersection is in the Borel sets on R2. We're almost done, I promise. So take any A in here and any B in here. We have shown that A crossed with B, which is a set in here, is in the Borel sets on R2. In other words, we have shown that the entire collection of Borel sets on R1 crossed with the entire collection of Borel sets on R1. Those sets are contained in the Borel sets on R2. But this, the sigma field generated by these sets, is the smallest sigma field containing these sets. And because this is contained in this and this is a sigma field, the sigma field generated by these guys must be contained in the Borel sets on R2. And that's what we wanted to show. So let's get back to vector-valued random variables. Remember, if we have an omega with a sigma field f, and we have maybe a k-dimensional vector-valued random variable consisting of components x1 through xk, this is going to take a point in omega. You're going to evaluate each of these individual functions at omega. You can think of this as an entire x of omega, where x of omega is defined to be x1 of omega, comma x2 of omega, etc. We're going to take in a point in omega and spit out a real number. The spaces under consideration here are a non-empty omega and a sigma field curly f, and rk and the Borel sigma field brk on the reals on rk. If this is a random variable or a random vector or a vector-valued random variable, we need the inverse images of Borel sets from rk to fall under this k-dimensional map back into curly f. This we already know, this is the definition, but I claim that this is equivalent to pulling back individual one-dimensional Borel sets under the individual components of this function. Showing this over showing this, I think, is generally a lot easier. Let's do the forward direction. Suppose that x, consisting of components x1 through xk, is a measurable function, is a random variable. This, of course, means measurable curly f slash the Borel sets on rk. This means that x inverse of b is in curly f for any Borel set b on the Borel sets in rk. Now note that for any xi, any real number xi, the inverse image of the interval from minus infinity up to xi, including xi, this can be written as the inverse image under the entire x map, where we want to pull back just an interval in one of the dimensions. So we're going to take that interval and cross it with the reals. Imagine a case where k equals 2. So maybe this is my x1 axis, which is the real line, and the x2 axis is another copy of the real line. If I want to know the set of omegas over here from some set omega that map under the first component into an interval from minus infinity up to some x1, I can look at everything that's going to map in this two-dimensional picture into this region. When I consider x1 alone, those are the points that are going to map into this interval. So what I'm trying to say is that the inverse image under the ith component of x of an interval like this, the points that map into this are the same points in omega that under X map into this bigger region. This region here, R crossed with R crossed with, and then one of these having an interval from minus infinity up to xi closed, is a Borel set in Rk. And because X is a measurable function or a random variable, I do know that this X inverse of a Borel set in Rk is in F. And that means equivalently, I know that the xi inverse function of just this interval is in F. And this means that xi is measurable with respect to F. So this is going to be an F slash Borel sets on R1 kind of thing. To go the other way, let's now assume that each xi is individually measurable. That means that if you take a one-dimensional Borel set and pull it back under one of the components of the x vector, the resulting subset of omega is going to be in curly F. Note that the Borel sets on Rk can be generated by rectangles of this form, so these minus infinity up to some closed number. By today's lemma, we know that the inverse image of any Borel set in Rk is going to be an F to show that we know it's enough to show that inverse images of sets like these are in F. So let's do it. Note that the set of omegas for which all of this stuff happens, this is the same thing as that inverse image set I had on the previous slide. This is the intersection of all points in omega for which each component maps into the appropriate place. Because you need all of these things to hold at the same time for each omega you plug in, and that's what the intersection is doing over here. We are in the direction where we're assuming each xi alone is a measurable function. And this set right here is the inverse image of an interval minus infinity up to xi under the function capital Xi. Now this is in F because we're in the part of the theorem where we're assuming that each xi is measurable. So the inverse image of all Borel sets under xi, and that's one-dimensional Borel sets, will be in F. And this is a Borel set. So right here, I've got a finite intersection of F sets. F is a sigma field, and it's closed under even countable intersections, finite intersections for sure, it's closed. And that means that this is in curly F. So what we've seen is that the inverse image of a generating set of the Borel sets in Rk falls in the right place. And by today's lemma, that means the inverse image of arbitrary Borel sets in Rk will pull back under the full function x into curly F. Next time, I'm going to prove the theorem that I stated today without proof that I said I wasn't going to prove until I got up to vector valued things. And we're going to see the relationship between a sigma algebra or sigma field generated by like x1 and x2 versus the sigma field generated individually by those x1 and x2. And after that, I'm not sure if it's the next video or not, but we're definitely getting into sequences of random variables and almost short convergence. So I hope to see you in the next one.